Welcome back. CalcBC, we're getting into section 12.2, and this is where it officially really begins. We're dealing with series. In 12.1, we actually were dealing with infinite sequences. But take a look at this definition right here. An infinite series is of the form a sub 1 plus a sub 2 plus and so on, all the way up to a sub n, assuming that you'd go on forever. In other words, what you're doing is you're adding up the terms of your sequence. You're adding up the first term, the second term, going on forever. This is the Greek letter sigma. And the Greek letter sigma is very much like our letter S standing for sum in this case. Sigma, if you look down below, this tells you your beginning, where you're going to start adding up your terms. When n equals 1, you're going to say start from the first term. You can see up here we go to infinity. This means go on forever. Just keep adding up, never stop. It's very important to note that many of the problems that you're going to see are just going to give you a sigma without any boundaries. That will still represent an infinite sum of the terms of the sequence. So it's what we were doing in 12.1, but we're actually going further. We're going to add up all of those terms. Here's another definition. The kth partial sum. Obviously, we don't have to, add up towards infinity. We could just say, hey, stop at the 100th term. For example, if you wanted that would be S sub 100. That would indicate add up the first 100 terms and so forth. So that's a way to denote just add up to this term. But the sequence of partial sums, if you were to say, hey, let's look at what happens when we just add up our first term, add up our second term, add up our nth term. If we're looking at that, we're looking at a sequence of partial sums. So if we're seeing a pattern, if our sequence of partial sums is going somewhere, if we're getting closer and closer to a fixed value by the sequence of partial sums, like looking at the first 100 terms added up, jump to the 1000th terms added up, and so forth. If you're saying, wow, I'm getting a sum that's getting closer and closer to something, that's going to allow us to say that the series itself is convergent. That is, if the sequence of partial sums converges, that is, the limit as n goes to infinity of s sub n is going to arrive at a fixed number s. So the limit, capital S, is that infinite sum where you would be getting closer and closer to a fixed number. You can say that this infinite sum is divergent if the sequence of partial sums diverges. So let's get in really to our first example. And you can see right here we have this summation from 1 to infinity, k equals 1 to infinity, of 1 over k plus 2 times k plus 3. Both of those expressions are in the denominator. So they're saying, would you find what s sub 1 is? So that, by the way, is just saying what is the first term. Well, the first term, when we let k equal 1, would get 1 plus 2. That would be a 3 down here. And 1 plus 3 would turn into a 4. And you could see pretty quickly that this would simply be 1 over 12. Now, s sub 2... well, that means start with k equals 1. So in other words, I can show step by step what that would look like. We already know what that first term is going to be. We saw that a moment ago. We realized that that's 1 over 3 times 4. But you see, s sub 2 says, you know what? Also add up that second term. So we'd have our 2 plus 2 times 2 plus 3. So this first term, that's 1 over 3 times 4, that's just 1/12. We already worked that out. Here we have a 4 and a 5. 4 times 5 is actually going to get you 1 over 20. So the second term in the sequence would actually be 1/20th, but now we're asked to add those together. It looks like a common denominator would be 60. So I could get this 1/12 is actually 5 over 60, and 1/20th, if I multiply by 3 over 3, I'd get 3 over 60, and I could wind up with 8 over 60. Of course, we could reduce that, and if we did reduce that, we could get a simplified answer, of course. You could divide out of 4, and I guess you'd get 2. 60 divided by 4 would be 15. So that's what the first two terms would add up to. You could say, what about S sub 3? Well, it's going to be take your first two terms right here, but then add on a third. And you get the idea. Now, as we continue to work this thing out, maybe the most pressing question is, are we picking up a pattern? By the way, the third term down here, that's 3 plus 2, that would be a 5, and 3 plus 3 would get you a 6. So in other words, we already know what these two terms are going to be adding up to. That's going to be 8 over 60 if we didn't reduce that. And then over here, this is 5 times 6, that's 1 over 30. And, we could realize that 1 over 30 is actually 2 over 60. 2 over 60 plus 8 over 60 is 10 over 60, and that just would become 1 over 6. So add up the first three terms, you get 1/6. Add up the first two terms, you get 2 over 15. Just add up the first term and you get 1/12. Here's the pressing question. Where are we headed? Or are we headed somewhere? If we kept adding up these terms, are we going to get closer and closer and closer to a specified number? Well, that's more or less what we're going to start answering when we find the general nth term. What if we just go up to an arbitrary stopping point? And right now, we might not see a pattern. It certainly would be rather confusing to try to pick one up. But let's just say, for example, that we look at this formula inside, the formula for the sequence, by the way. And if we said, my oh my, this reminds me of last chapter with partial fractions. Wow. Now, partial fractions, of course, helped us integrate. You might wonder if partial fractions might help us with this series question. Indeed, it will. As I multiply through by an LCD, we'd have A times K plus 3. And here we'd have B times K plus 2. And tell you what, I'm going to continue up here. Let's let K equal -2. And if K equals -2, of course, this B expression cancels out. -2 plus 3 is 1. You'd have 1A equals 1, or A is just 1 itself. Let's let K equal -3. If we did that, the A term would just completely cross out. You can see that. You'd have 1's equal to -B, indicating that B would equal -1. So B appears -1, A appears 1. In other words, here's a sigma, and I've got 1 over K plus 2 minus 1 over K plus 3. Sometimes kids are wondering, why in the world are we even, doing this? Well, we need some help. We're looking at these partial sums. We have no idea where we're going. And a partial fraction, maybe, just maybe, could help us as we arrive at a sum up to an n term. So adding up n terms, wow, we don't even have a specified number. But look what happens when I start working this thing out via this new formula. I'm going to just plug in the numbers directly. 1 plus 2 is 3, so my first term I'll get 1/3, minus, plug in the 1 here, 1 plus 3, you get 4. So, we're starting with K equals 1. That's the first term. Let's plug in a second term. You get 1 over 2 plus 2. Well, that's a fourth. Plug in the 2 here. You get 2 plus 3. You get, 5. 1 over 5 there. Let's go to our third term. You say, well, let's see, 3 plus 2. That's 1 over 5. 3 plus 3 is a 6. You get the idea. We could keep going. And, as we would continue to go, eventually we're going to stop with an nth term. We'd get 1 over n plus 2, 1 over n plus 3. Now, I want you to take a close look here and see what's happening. A minus 1/4 would cancel with a positive 1/4. A minus 1/5 would cancel with a 1/5. Here's what I'm getting at. If you just stopped here at the third term, you'd see that the first term in the parentheses, the first expression there, would get canceled out. We're going to continue to get this canceling. Look, I'm stopping right here. This would wipe out. You'd say, oh my goodness, look at this, all this collapsing. What we're seeing is, what do you get when you add up the first n terms? Well, it appears that I'd get 1/3 minus 1 over n plus 3. Wow. Wow, and you can wonder, is that really right? Is that really correct? Well, look, just a moment ago we found our third term. If n's equal to 3, let's check that real quickly. We'd say, well, that should be 1/3 minus, 3 plus 3 is 6. Double that, you get 2 6 minus 1 6. Look at that, you get it. You have found a formula for adding up however many terms you need. This is called, guys, a telescoping series. That can sound so strange. Telescoping series. You can think, why in the world is it called telescoping? Well, you might remember, if you've seen some movies in the past, especially something like Pirates of the Caribbean or something like that, where people, and by the way, this math was developed hundreds of years ago, when the primary way to travel would be long distances. You'd have boats. You might remember on the Pirates of the Caribbean, they'd have a spy scope, on a ship, and they'd look far off, and then all of a sudden they could collapse it. You could push on that and it would collapse. That's why this is called a telescoping series. You've got this huge expansion, but it's all going to cancel down. It's going to collapse down to something very nice and concise. Well, how about for part C? Show that this limit converges. Well, what we're going to be able to do is say, well, where are we headed if we get 1/3 minus 1 over n plus 3? We're going to add up the first n terms. Well, my goodness, this sum is going to approach 1/3.